Okay, G5. All right, so this is one of these little weird little problems where I've given you certain bits of information in sort of in a non-typical order. Right? And what you have to do is take the information given, write it down in whatever way you can, and then interpret in whatever way you need to. So we've got this, conveniently we have a continuously differentiable function, so we know that every nice thing that we could hope to happen about differentiability happens. Everything's good. No sneaky little problems. We're told the direction of fastest increase is in the direction of some little vector there, 3, 4, 12. All right, so let's draw a little picture. Got some point there. And 3, 4, 12, let's say, goes about like that. And I know the direction of fastest increase is in that direction. And right off the bat, I know that the gradient is going to be some vector in the same direction, because the gradient always points, the gradient always points in the direction of fastest increase. Now, the problem didn't say that this is the gradient vector. It's just that this is in the direction of fastest increase. Does that make sense? So what I really know then is that the gradient of f, in other words, partial of f with respect to x, partial of f with respect to y, partial of f with respect to z, that is some multiple, some unknown multiple of 3, 4, 12. Okay. Everybody on board? Okay. All right. Okay, next, I'm also given that the rate of change of f with respect to distance traveled in the x direction is 7. Okay, so as I move in the x direction, this is supposed to be parallel to the x-axis here. And let's see, a rate of change of f with respect to distance traveled. So that means unit directional derivative. So that tells me that unit directional derivative in the E1 direction of f is 7. Well, of course, now wait a second. This is partial of f with respect to x. Is that cool? Okay, so notice what all I've done is I've taken the two givens. I've got this one given fact about this vector, another given fact about that. I didn't mean to draw these as looking kind of parallel. This is supposed to be going up at some angle, and sorry about that. But I've taken these givens and I've interpreted accordingly and drawn some conclusions about the algebra of this function, the partial derivatives of this function. So altogether, I claim that I have enough information to determine all these partial derivatives. Right? Because I know the partial of f with respect to x is 7. Since that's 7, that tells me what k is. This k, 7 is equal to k times 3. That means k is equal to 7/3. And if I know what k is, then I know all these partial derivatives. Does that make sense? Mm-hmm. Is everybody happy with that? How are we doing? Okay. So now that we've understood our givens, the problem says, okay, well, what's the largest unit directional derivative of f at that point? Okay, so all right, fine. In what we already know, the direction of fastest increase is the direction of that vector. I want to know now what is the directional derivative in that sort of optimum direction? All right. I want to know what is the directional derivative of f in the direction of fastest increase. That's the problem I'm being asked. Now, remember, this is the answer to one of the questions that we talked about in the gradient section, right? So this is one of the properties that the gradient has. The answer to this question is, I'm going to say this is a property of gradients. That is equal to the length of the gradient vector. Is that cool? Everybody remember that property of the gradient vector? Okay. So all right, so I just want to compute the length of the gradient vector. Well, fine. Well, here's the gradient vector. Now I'm going to have to do a little arithmetic to see exactly what this length is, but I mean, I could compute these individual elements by knowing k and knowing these numbers. I'm going to do this in a slightly slicker way. I mean, one thing you could do is explicitly compute all these derivatives and then compute that length. Here's a slightly slicker thing I can do. The length of the gradient vector. Well, that means I'm looking for the length of k times 3, 4, 12. K is positive, so I can factor that out. I have k now times the length of 3, 4, 12. You can do some arithmetic and confirm for yourself that this is 13. Is that cool? That's just arithmetic. But it's integer arithmetic, so it's kind of convenient. And so what I've got is k, which I already computed with 7/3, times 13, and that gives me, oh gosh, let's see here, 91/3. That's our answer. Yep. Everybody happy with this one? Okay.